In this video, we talk about the section 6.4. Logarithmic function. Okay. What is a logarithmic function? We know that in the exponential functions, we see this is a graph of the y equal to a to x. Y is equal to a to x. Here a is greater than 1. And when a is less than 1, it looks like this, between 1 and 0. And in this case, function is increasing. This case, function is decreasing. But it doesn't matter function is increasing or decreasing, they are both 1 to 1. Okay, so we know that for 1-to-1 function, we can define the inverse function. So the logarithmic functions are the inverse functions of an exponential function. Okay. The exponential function has a base. Logarithmic function also has a base. So the logarithmic function to the base a, where you see here a is greater than 1, a is greater between 0 and 1. So here we also have a is greater than 0 and a is not equal to 1. Just copy the condition here. Okay. Is defined by y equal to log ax. Y is the logarithm to the base of a of x. Denote, not define. This is a denote. Denoted is defined by y is equal to log a of x, the logarithm to the base of a of x, the logarithm to the base of a of x, if and only if x is a to y. X is a to y. X is a function of y as an exponential function. Y is a function of x as a logarithmic function. Okay. X is a function of y as an exponential function. Y is a function of x as a logarithmic function. Okay, so x is here. X is a range of exponential function, and so it is a domain. The domain of the logarithmic function is x greater than 0, because here is a range. The range of exponential function is greater than 0, so here the domain is greater than 0. Okay. For example, if you have y is log the logarithm to the base 3 of x, if we have symbol like this, the logarithm to the base 3 of x, then it means x is 3 to y. You move this base 3 to the left side, you lift y to the exponent. Okay, so when you move 3 to the left side, 3 becomes a base, you lift y to the exponent. And for example, we got, because 3 to 4 is 81, the fourth power of 3 is 81, then we take the logarithm to the base 3 of 81 is equal to 4. We want to know the power to the base of certain number. So the value is the power. Okay? And for example, let's choose y as logarithm to the base 5 of x. Then we get x is 5 to y. Y is its exponent. And 1 over 5 is written as 5 to negative 1. So log to the base 5, 1 over 5 is equal to negative 1. We want to know what is the corresponding exponent for the 1 over 5, for the number 1 over 5, to the base 5. Okay, to the base 5. Also, for example, if we have log 2 of 16, we know that 2 to 4 is 16, so the value is 4. 2 to 4 is 16. And the logarithm of 16 to the base 4 is equal to 2, because 4 squared is 2, right? So for different base, you have different value. It's sure the correct thing, the reasonable stuff, right? So what we do is that we just want to check what is the corresponding power for this value to the base. Choose this base, what is the corresponding power? Choose this base, what is the corresponding power? So that is a logarithmic function. Okay, so let's see more examples. It's an interesting writing, so we have to be familiar with this writing. For example, if we get 1.2 cubed is equal to m, then how do we write the logarithmic function? Then the logarithm to the base 1.2, base is always a base, of m is equal to 3. Okay, so you put base here, and m corresponds to the exponent 3. And b, if the e to 6 will be a b, e to b is 9, e to b is a 9, then the logarithm to the base e of 9, of number 9, is equal to b. Okay, and assume a to 4's power is equal to 24, then the logarithm to the base a of 24 is equal to 4. Its corresponding exponent is 4. Okay, so that's a writing from exponential function to the logarithmic function. And from logarithmic function, the logarithm to a of 4 is equal to 5. Assume we have this number. This means a to 5th power is equal to 4. a to fifth power is equal to 4. This is power exponent. And if log, what's that? Okay, logarithm to the base e of b is -3, then this is a value. This is exponential evaluation. You lift it to the exponent. Whenever you have this, you just lift it to the exponent. Base to the exponent is equal to the value. Okay, and if we have a logarithm to the base 3 of 5 is equal to c, then what we got is that 3 to c's power is equal to 5. Okay, so that's just like back and forth writing that help you to understand what is the definition of a logarithmic function to the base a. It is the inverse of the exponential function. Okay, so and if we have logarithm to the base 2 of 32, if you can recall the multiplication table, you will notice that 2 to 5 is 32. 2 to 5 is 32. So this is equal to 5. 32 corresponds to the 5. And if you have logarithm to the base 3 of 1 over 27, we know 3 cubed is 27. But now it's in the denominator. In the denominator, you have to flip it. You put the negative sign. 3 to -3 is 1 over 27. So this 1 over 27 corresponds to the exponent of -3. So the value is -3. So how to evaluate the exponential function? You have to go back to the, how to evaluate the logarithmic function. You have to go back to the exponential function and try to find the corresponding exponent, if it is possible. Okay, if it is possible. Of course, you can write them as an equation. How do we write it as an equation? For example, let's choose G. G, we let y equal to the logarithm to the base 2 of 32. We let y equal to this. And then, by the definition of a logarithmic function, this means 2 to y is equal to 32. 2 to y is equal to 32. And 32 is 2 to 5. Still, you have to recall the multiplication table. 32 is a 2 to 5, so 2 to y is equal to 2 to 5, and by the solution of exponential equations, we get y is equal to 5, because they have the same base, then they have the same exponent from the equation. Okay, so. So that's the rough practice for the definition of a logarithmic function. Because in a logarithmic function, there's so many stuffs and letters, numbers, so don't be confused with the definition. It's just inverse of an exponential function. Okay. Because it is the inverse of the exponential function. Let's see, for the exponential function, the domain and the range. And for the logarithmic function, the exponential function has domain negative infinity to positive infinity, range from 0 to positive infinity. Because it's an inverse, so the domain of a logarithmic function is from 0 to infinity, and its range from infinite, negative infinity to positive infinity. You just exchange the domain and the range, right? So it's a property from the definition of pairs of inverse functions. Okay, so this is a domain, and this is a corresponding range. Because you see here, if you have the base 3, then 1 over 27 has a value negative 3. So the value could be negative. You just have a negatively large power. You will have if you have put a negative large power, then in the logarithmic function, you will have a negatively large values, right? For example, if you put 3 to negative 100, then this part will be negative 100. If you put here 3 to negative million, then this value is 3 to negative million. So it could be as negative large as possible. Okay? It's just exponent. Exponent can be negative, but the domain is always positive because after you evaluate the exponential function, the value is always positive. So for the logarithmic function, the domain is positive. Okay, so let's see. We have fx as the logarithm to the base 2 of x plus 3. Then what is the domain of this function? The domain of this function is a set of all real number such that x plus 3 is greater than 0. So whatever inside it, the expression has to be greater than 0, because the domain of a logarithm is greater than 0. Okay? So you put x plus 3 greater than 0, you get x greater than negative 3. So the domain is negative 3 to infinity. Okay? Negative 3 to infinity. Second, assume we have this function g of x as a logarithm to the base 5 of 1 plus x over 1 minus x. We change the base. It doesn't matter what base we choose here. And we require the internal expression is positive. We require this internal expression to be positive. Okay, so how do we get the solution? You see, you have a ratio, the ratio is positive, so you will have possibly you have both positive numerator denominator, positive or positive is positive, or both negative numerator over negative denominator is also positive. So this is equivalent. The quotient is positive. It is equivalent to the product is positive. Okay, so that's a very important stuff. A quotient is positive. It is equivalent to the product is positive. We are talking about the inequality. We're talking about the inequality. Okay, and how do we solve this one? This is a quadratic function. Let's check what we can have. First of all, if you multiply it out, you will get 1 minus x squared. Right? You see 1 times, let me complete this. It's a 1 minus x, 1 times 1 times negative x, plus x, times negative x is negative x squared. So you cancel the middle two terms, you get 1 minus x squared. And this is a quadratic polynomial, but this is not the usual quadratic polynomial we study. We remember when we use a quadratic polynomial together with the inequality, we assume this leading term is positive, here is negative, so we multiply this inequality by -1. We just memorize the formula for the positive leading term. Okay, so we multiply all the terms by -1, we change the direction of inequality. So basically, we want to study this inequality, x squared minus 1 less than 0. You factor it, it's x plus 1, x minus 1 less than 0. You have two solutions. This is x equal to -1. This is x equal to 1. So two solutions. Because it is the leading coefficient is positive, it is opening up. So the solution is between -1 and 1. When x is between -1 and 1, this is positive, this is positive. So that's is a domain. So don't forget what we are computing. We are trying to find a solution, and this solution is a domain of our original function. Okay, so we're looking for the solution of inequality, not the solution of equality. These two values are, of course, different. The quotient, the product are different, but these two values will share the same sign. We are trying to focus on the sign, not on the value. Okay? And also, from here, you cannot say, okay, 1 minus x give you 1, 1 plus x give you solution -1. Then it is greater than 0, so it's greater than 1 or less than -1. That's wrong, because this product has negative leading coefficient. Okay, it has negative. You must have positive leading coefficient in order to recall the graph and find the answer. Okay, h of x is equal to the logarithm to the base 1/2 of absolute value of x. Again, we require the absolute value of x is greater than 0. But we know that absolute value of x is always greater than or equal to 0. So basically, we have to remove that equal case. Equal to 0 is not allowed. So this means x cannot be 0. Only when x is equal to 0, its corresponding absolute value is equal to 0. Okay, so x is not 0. So the domain is -infinity to 0, union 0 to positive infinity. So we just use the round parentheses to remove 0. Okay, so that's the computation about the domain. Okay, now let's see the graphs. Let's see the graphs. We know that the definition of the logarithm function, logarithmic function, is the inverse of a exponential function. And we also know that if you have a pair of inverse functions, then their graphs are symmetric about the line y equal to x. So we first sketch the line y equal to x. And for example, let's assume a is greater than 1. A is greater than 1, the exponential function looks like this. So this is number 1. Okay, assume it looks like this. And then we try to sketch the corresponding logarithmic function. So 1, 0, 1. This is 0, 1. X is 0, y is 1. The symmetric point is 1, 0. This is a symmetric point. And you just try to get the symmetric image. Okay, so this, sorry. Yeah, this is a y equal to x. This is a to x. Then this is a graph, the logarithm of to the base a of x. Okay, this is also 1. Here's 1, here's 1. You see, we just use the symmetry to sketch the graph of a logarithmic function. When a is greater than 1. This is a case when a is greater than 1. When case a is less than 1 and greater than 0, when a is between 0 and 1. Okay, this is number 1. So a to x, a is between 0 and 1, and y equal to x. This is number 1. And we first get the symmetric point. Now we have this. This is a graph y equal to the logarithm to the base a of x. Logarithm to the base a of x. Okay, so let's see the properties of a logarithmic functions. Okay, let's do it one by one, and we'll explain. Properties of a logarithmic function f(x) equal to the logarithm to the base a of x. Okay, the first property, domain and range. Domain 0 to infinity. The logarithmic function is only defined for the positive numbers. Range can be as negative infinity to positive infinity. And second, this is a 1. This is also 1. So the x-intercept is 1, always, for whatever base. And there is no y-intercept, because 0 is not in the domain. You see here, 0 is not in the domain, there's no y-intercept. Okay? And 3. In the exponential functions, x-axis is a horizontal asymptote. So after symmetry, y-axis is a vertical asymptote for the logarithmic function. So y-axis is a vertical asymptote of the graph. And y-axis has the equation x equal to 0. You can say x equal to 0 is a vertical asymptote, or you just say y-axis. Okay? 4. in the property 4, we have to distinguish the values of a. So if a is greater than 1, if a is greater than 1, it's an increasing function. The logarithm to the base a of x is increasing. If a is between 0 and 1, the logarithm to the base a of x is decreasing. Actually, for the exponential function, when a is greater than 1, it is also increasing. In this case, it's also decreasing. So here we actually have a general case, a general conclusion. If y equal to fx is increasing, then y equal to f inverse of x, the inverse function, is also increasing. Increasing property is preserved between the inverse pairs. One is increasing, the other one is also increasing. And of course, one is decreasing, the other one is also decreasing. Okay, so this is one of a general property. It's not just for the exponential function, the logarithmic function. Okay. And 5. There are several fixed points. So you have this point. X-intercept is 1. It means when x is 0. When x is 1, y is 0. So when x is 1, y is 0. And we know that, you see, a to 0 is 1. A to 1 is a. A to -1 is 1 over a. This is a power, exponential. And if we write logarithmic function, log a of 1 is 0. Log a of a is 1. Log a of 1 over a is -1. Okay, so we get 1, 0. A, 1. 1 over a, -1 are on the graph. A corresponds to the power a to 1. 1 over a corresponds to the power a to -1, so that's why you get a -1. 1 corresponds to the power a to 0, so you have 0. Okay, and the final thing is that the graph is smooth and continuous. No corners or gaps. No corner means it's smooth, no gaps means it's continuous. Right? So this is the basic property of a logarithmic function, the logarithm to the base a of x. Okay. In the exponential function, we have a special numbers. Do you still remember that special number? E. E is the limit n approaches infinity, 1 plus 1 over n to nth power. It's approximately some number like this. And we have y equal to e to x. We call it the natural exponential function. Okay, still it is an increasing function. It's just a special choice of base a. And For this natural exponential function, its corresponding logarithmic function is called the natural logarithm function. It's a natural logarithm function, and we use a special symbol. We do not write log ex. We write ln x. ln x is a natural logarithm function. Okay, so in the future, whenever you see ln of x, it just means the logarithm to the base e. Choose this e and apply the logarithm function. Okay, so y equal to ln of x is equivalent to x to e to y. Okay, this is the natural logarithmic function and the natural exponential function. Okay, so now let's put the exponential function in the computation system. So we want to find the graph. No, find the domain, not the graph. Find the domain of fx is equal to negative ln of x minus 2. Find the domain. Well, it doesn't matter which base you choose. You choose a, you choose 1 over a, you choose e, you choose 1 over e, you choose whatever stuff. The domain is a set of all real numbers so that x minus 2 is positive. Okay, so it is x minus 2 positive, x is greater than 2, so it's from 2 to infinity. It's from 2 to infinity, so this is the domain. Graph this f. Graph this f. Well, let's see how do we graph it. Recall what we had. We had this graph. Okay, this is a graph of a logarithm to the base a of x when a is greater than 1. And now we use e. E is greater than 1. So this is a graph. ln of x, first step. And second, x minus 2. X minus 2, we are going to translate the graph horizontally 2 units to the right. 2 units, this 1, 1, 2, 3, 3 is here. And the y-axis is moved to this place. Okay, so this is a log x minus 2. And you put a negative sign. Negative sign means you're going to reflect it about the x-axis. One, two, three, 2. This is a vertical sum total. You reflect it about the y-axis, so you get this. See? So this is a graph, the final graph. You do one translation and one reflection. And this is x equal to 2. And from this graph, we can determine, you see, it's always on the right side of 2, the domain from the graph. We can see that the domain is from 2 to infinity, also from 2 to infinity. The line x equal to 2 is the vertical asymptote. So if a graph has certain asymptote, when you do this translation reflection, it's better for you to also sketch them here, because those asymptote line will help you to sketch the graph. Okay, this is asymptote. And D, not D. Find the inverse. Find the inverse of f. The same thing. Negative log x minus 2. How do we find the inverse? Do you still remember it? So we first put y equal to negative log x minus 2. This is the first step. And second, we exchange x and y. Only symbols, exchange x and y. So we get x is equal to log y minus 2. Okay? And then we solve y in terms of x. Right? So how do we solve it? We first move negative sign to the left side. It becomes negative x is equal to the log y minus 2. The logarithmic function is equal to the value. So by the definition, this is exponent. So ln means the base is e to negative x is y minus 2. E to negative x is y minus 2. Okay? And then you move 2 to the other side. So e to negative x plus 2 is equal to y. So f inverse of x is equal to e to negative x plus 2. Right? This is the inverse. This is the inverse. And for the inverse, we see here the domain is, well, exponential function has no restriction. So exponential function has domain negative infinity to positive infinity. The range is, exponential function is greater than 0 plus 2. The sum is greater than 2. So it's from 2 to infinity. So you see, this range is exactly the domain of our original function. Exponential function is always greater than 0 plus 2 is greater than 2. Okay? And if you want to sketch the graph of exponential function e to negative x plus 2, let's try it. Original exponential function is this way. It's e to x. E to negative x, you reflect it about the y-axis. E to negative x plus 2, you lift it vertically 2 units. 1, 2, 3. 2 units. First, I sketch the horizontal asymptote. Remember that x-axis is horizontal asymptote, so I lift it. And second, I sketch this graph. Okay? So this is a e to negative x plus 2. This is the final graph. If you put these two graphs together, they are really symmetric about the line y equal to x. Okay, this is a graph of inverse. This is a graph of original function. They are symmetric about the line y equal to x. Okay, so see, we just do whatever we have done, but for the new family of functions, we put the exponential function and the logarithmic function in our computation system. In our computation system, what do I mean? I mean, we can find the domain, we can find the range, we can determine the graph, we can move the graphs, we can find the inverse. Now we just do it for the logarithmic function, the exponential function. They are a perfect pair of inverse functions. Okay. And next, e to x, then that special number e has a great application in the calculus. But in our common computation, we also have another important number, 10. Okay, so for a is equal to 10. 10 is our unit, like 10 squared is 100, cubed is 1,000, stuff. So for a equal to 10, the log 10 of x, we just ignore the 10. When a base is 10, we just ignore it. And this logarithmic function is called the common logarithm function. Common logarithm function. Okay, so log x, if you don't see the base, it just means the base is 10. If you do not see the base, then base is 10. Okay. So, well, I have to make it clear. This number, this symbol possibly will change if you change your textbook. So be careful about the notation. This notation may have different meaning or different expression. So when you have this common logarithm function, pay more attention about the symbols. Possibly some people will use a different symbol to represent this common logarithm function. This name is widely accepted, but maybe, I just say maybe, you will use, some people will use different symbols to represent it. Okay? It's not like that ln of x. ln of x is just ln of x. All the people use that symbol. Okay? Okay, so next, let's try to solve logarithmic equations. Logarithmic equations can only be solved by exponential equations. Okay, so you always write logarithmic function as the exponential function and logarithmic equation as the exponential equation, and then solve it. Okay, so for example, we have a logarithm to the base 3 of 4x minus 7 is equal to 2. How do we solve it? How do we know the value of x? Logarithmic function to the base 3, it is equivalent to 4x minus 7 is equal to 3 squared. This is power. 2 is the exponent. 3 squared is 9. Okay, 4x minus 7 is equal to 9. So this is a simple linear equation. So 4x is 7 plus 9, 16. So x is 4. So this is the answer. Okay, this is the answer. So we always translate logarithmic equation to the exponential equation. And another one, logarithm to the base x of 64 is equal to 2. logarithm to the base x, 64 is equal to 2. And by the definition, 64 is equal to x squared, x to second power. 2 is the power. And we're going to take square root, positive and negative. It has to be positive because x is a base. X is positive, so we take the principal square root. So x is 8. X is 8. Okay, so be careful when you have this variable base, then the base has to be positive. Okay. Okay. This is the logarithmic equations, and sometimes we can use logarithmic numbers to represent the solutions. For example, if we say solve e to 2x equal to 5, how do we solve it? To solve this, exponential function is equal to 5. You don't know the power. It's a job of a logarithmic function. So by the definition, power is equal to ln of 5. Base is e. The corresponding value is 5. So the ln of 5 is 2x. And you divide two sides by 2. And that's it. Well, this is an irrational number. We have no idea about the true value. It's just a ln of 5 over 2. It's a symbol. Okay? Let's do more examples. For example, if we have what we have, if we have e to negative 2x plus 1 is equal to 13. How do we solve it? We transform this exponential function to the logarithmic functions. Negative 2x plus 1 is equal to ln of 13. And now this ln of 13 is just a number. We don't know the true value, but it's a number. It's represented by logarithmic functions, but it's a number. When we consider it's a number, let's see, we move 1 to the other side. And we divide this by negative 2, by the coefficient of x. And that's it. This is a solution. Right? And for example, if we have logarithm to the base 5 of x squared plus x plus 4 is equal to 2. Okay? Well, let's check. So this logarithmic equation, so x squared plus x plus 4 should be equal to 5 squared. Should be 5 squared. So you move 25 to the other side, x squared plus x minus 20 minus 21 is equal to 0. Well, this one, you have to use the root formula. 2 negative 1 plus minus square root of b squared minus 4ac. Right? So it's a 4 times 4 times 21 is 84 plus 1 85. So there are two solutions. X is equal to negative 1 plus root of 85 over 2. Or x is negative 1 minus root of 85 over 2. Do I make a mistake or not? square is 25, move to the negative 25. 4 minus 25 is 21. Okay, yeah, I don't make a mistake. Okay, so this is the solutions. So when you have logarithmic equations, you just transform it to the exponential function and do the rest of the jobs. And if you have an exponential function, you're trying to evaluate the variable exponent. You transform it to the logarithmic function, and you will have some weird irrational number, but it doesn't matter. It's just a number, and then you represent the answer in terms of logarithmic numbers. Okay, so that's the section 6.4. The section 6.4, we study the basic definition and the basic property of logarithmic functions. Okay, so do the exercise, make sure you understand the steps. Okay, and send me email if you have a question. We'll stop this video. We will continue in the next video. Thank you.